All right, recording is rolling. Welcome to Thursday, September 21st. Got a few points of school news. I'm going to do elevator wait with you guys, which is there's a connection to the lab you guys did yesterday, Atwood Lab. Okay? And then we'll do FRQ near the end of class period. You guys have it on your desk already, actually. But so it'll be a little bit tight fit. We're going to do that. All right, here's you guys' upcoming due dates. Okay, you guys got due dates? All right, so first thing, tomorrow's going to be a bit of a weird day. We've got this reunification drill going on. This is going to be in, I think, like first and second period supposed to. So, right, tell you guys best as I know what's going on. I think this is a drill. I don't know if it's from the district or from the state, but it's something to do with the idea like if there was some catastrophic event like a school shooting, like how we're going to manage all the students and eventually reunify you with your parents. So, I think how this is rolling out is you go to your first period class, you'll be there like maybe like 5 minutes just for attendance, right? And then some pretty early on, they're gonna announce this drill. They're gonna start rolling this out, right? Maybe some of you guys know from earlier today, right? Because this will happen tomorrow, right? Do you guys know where you're supposed to go tomorrow?
No.
The gym. Go to the gym. Right. So you'll be in your first period class for like 5 minutes. Right? Then they'll dismiss you guys. Right. And then the entire school of students, just all the students are going to be in the gym, just be in the bleachers. Right. If they want you to do something after that, then they'll let you know. But that's as much as I know there. Right. Now, all the teachers, so some of the teachers might go there, but you're probably not going to be escorted because a lot of the teachers are going to be in other stations. Like I know I'm assigned to be like in the bus loop doing something there. Okay. Right. So we got that. Right. And you guys are going to be in the gym. Right. I do have some directions. Here, I'll show you guys. Right. Maybe not super thoroughly, but right. We got let's see, front office, administration there, reunification area. IDs. You guys should be bringing your IDs to school every day, but are you guys definitely going to bring your ID tomorrow? Right, ID, yeah. So definitely bring your ID tomorrow. Right? Everybody's going to bring their ID tomorrow because that might be part of the process. That again, it's like a trial run, so supposed to do that. Right? They might be checking your IDs. All right, we got here. You guys mainly care about this student staging area in the gym. All the students are going to be in the gym, right? And then a handful of teachers to help monitor you guys there. Some other stuff going on in other places. How they've got this is parents are supposed to come in the auditorium, right? So auditorium, parents going through there, and then I think they are supposed to like reunify you guys in building one. It looks like best I can interpret this. Right, so I think that's what's going on there. All right. So you guys got that? Oh, and since that's gonna throw all my class off otherwise, because it might be like 1, 2, 3 class periods. Yeah, we might do something a little bit different tomorrow. I don't know. We'll see. I got some ideas, but anyway. Okay, so, right, next thing is Blue Book. Blue Book. All right, so you guys have student laptops. They want. This is an email from school. They want all the students to download this program called Blue Book from collegeboard.org. So you're supposed to go to collegeboard.org, create an account. Now, you guys in front of me, all of you already have an account in College Board because you guys are AP, right? So College Board does AP too. Right? You're supposed to download this Blue Book app. Please switch my screen over and show you guys exactly the place I put this link. Right? Yeah. If you guys are getting your planner out and writing that down, that's a good idea, right? Right, so here's Google Classroom. It's the last thing I posted. I posted this last night. Right, so here's our daily class videos. Right, so I put for you guys here. Go to collegeboard.org. Right, you guys have an account already. Okay, download the Blue Book app. Know your College Board info. Okay. So some standardized tests coming up. We're going to go through Blue Book. They're trying to switch from paper pencil to digital. Oh, yeah, Reese. Oh, okay. I'll have to look for that later. I don't. Okay. Yeah. All right. So there's a couple applications of this coming up. Right. This Blue Book. On Monday, there's going to be a readiness check and first period. Readiness check Monday, first period. Right. I don't know exactly how it's going to roll up, but I'm imagining something like first period, maybe like a few minutes into class. Maybe they'll make an announcement, say everybody pull up your laptops, and we'll do this readiness check. Okay. The application after that is mostly for 10th graders. There's a PSAT coming up, all the 10th graders, but also a few students from other grades too, right? They'll be taking the PSAT, but the PSAT is not going to be paper pencil. It's going to be through Blue Book, through laptops. Okay, all right, so you guys got that? Right, so you guys got in your planners, you're gonna download Blue Book. All right. Okay, here, let me show you here. All right. Right, College Board. Okay, so on Google Classroom right here, I posted here, collegeboard.org. It's somewhere collegeboard.org. That's as much as I know. Right, so Blue Book. All right. All right. Next thing. Ooh, I always get one of these ballots every year. All you teachers have one of these ballots. Ballot for Teacher of the Year. Now, I have not had any classes with any of these teachers, but that you guys have. And so what I do every year is I pull all my students, all my classes, for who they think deserves Teacher of the Year. I'll check one of these boxes and then submit it from there. And this is also a really good opportunity. I can tell you guys about voting systems, how different voting systems work. Right? So based on the rules of how you vote, you can get different voting environments. You can get actually different election outcomes too. Right? So I'm going to do an activity with you guys. I'm going to have you guys do like a show of hands. We'll do some voting, right? And I'm going to focus on just two voting systems. One that's called first past the post, right? And another system type we'll look at is called ranked choice voting. Okay. Right. Actually, if you rank your choices, there's several different ways you can process them. We're specifically going to look at a subset called instant runoff. Right. Instant runoff. Right. Okay. Right. So I want to do this process, and like during the process, I'll show what these different rules are and how they might lead to different outcomes. Right. So here we got a list of names. We got 8 names up there. Like, does everybody see a name in mind that they think, ooh, like I want like that teacher to be teacher there? Right? Everybody got someone in mind? Okay. Now I'm gonna do show of hands. I'll go down the list and see show of hands. Right. You get 1 vote. Right. 1 vote. Right. Now vote for whoever like you really want to be teacher of the year. Don't worry about how everyone else is voting. Let me give you guys an example. Suppose just for example, like you really like Miss Barnhill. Oh yeah, Miss Barnhill would be really good for teacher of the year. Right? But maybe I'm the only one who thinks that. And maybe, for example, there might be a close runoff between like Monroe and Moreland. And if I vote on Barnhill, then maybe I'd be like throwing away my vote. And then it could be like more useful if I put it towards Monroe or Moreland because maybe I have an opinion between those two and that's gonna be like a close race, something like that. Okay.
Is that how the 2-party system works? You have 2 voting days so that how many of the other ones actually matter?
Yeah, it's sort of the reverse. Like where does that system come from? It comes from the fact that the rules are crafted a certain way, so that if you like try to deviate from that, yeah, it would hurt your chances. Yeah.
Doesn't that then defeat the point of voting by just people not to vote what they actually want to vote, but rather choose between 2 that might be not so good?
Exactly. All right. Yeah. So you're getting on to yeah, something that once you guys get out of this. Yeah. So you're making a really good point. Yes, that's kind of where I'm going with this. All right. So for now, all right, we're gonna do like a first ballot, but vote for who you really want, and don't worry about like being the only voter, anything like that. So really who you want. Okay. All right. So everybody got someone in mind? Here we go. Let's do votes for Barnhill. Show hands for Barnhill. Who wants Barnhill? Got 1. Okay. So 1 vote for Barnhill. How about Contreras? Votes for Contreras. All right. Got one vote on Contreras. How about Monroe? Votes for Monroe. Monroe. Votes for Moreland. Got 1, 2. Right, 2 votes on Moreland. Velasquez. Let's vote for Velasquez. Right. It's for O'Boyle. Votes for O'Boyle. Dravis. Got 1, 2, 3, 4, 5, 6. 7. Looks like 7 on Dravis. Right. And Wayne. He's voting for Wayne. Got 1. All right. One vote on Wayne. All right. So yeah, I've been doing this all day with my classes, so I can show you some of the results from earlier to show kind of a point I'm making here. But right, if I say like who got the majority, you guys would say Like definitely Dravis, right? Because in this case, what's the definition of majority? It's not the most votes. It's more than 50%, right? And there's a difference there. Let me show you guys an example from last class how this panned out. Right? The first well here I scratched out, but right, the first run we were doing, but you can see the numbers there. Looks like Wayne had 6 votes, but there was actually no majority because if you add up the other votes, it adds up 5, 6, 7. Right, so there's 7 votes here and 6 here, right? So nobody had the majority, but like Wayne had the plurality, right? Now you guys, Dravis actually has the true majority, right? Now, if you have a system called first past the post, does anybody know what the criterion is for winning in that type election? Right? It's just getting the most votes. That's it, just the most votes, right? Which if you have the majority, it doesn't make a difference anyway. But if you only have the plurality, like my last class, like Wayne had the plurality, but not the majority, right? She would win for that. Now, one of the problems with that is that you could possibly have like a minority win, right? Like if you only have like 40% of the vote and then everyone else is split like just 20 or 30% or something, right? Then you don't actually have like a true majority. And it could be here. Let's look at last class so I could make the point a little bit better too, right? Is like if you look at everyone else added up was like, well, there's like 7 votes here, right? And we did a second vote, kind of like a primary sort of deal, right? Like a primary in general, right? And it turns out that like these 2 votes, like their second choice ended up being Dravis. So Dravis actually ended up having majority, like once you like do some iterations, right? Yes, that, right? So there's this idea called spoiler effect, right? Like if you start off with 2 and then some other people jump in the race, then you know they're probably like their voters like taking votes away from like who would have a good chance of winning, who might more likely be closer to them, say on an ideological spectrum, right? Like if you're voting for candidates for like public office, right? These aren't just people like personalities. They also come with like ideologies and platforms attached to them, right? So by having lots of people that are close together and similar type ideology or similar type platform, right? The more people running, it actually hurts their own ideology, hurts their own platform, right? And someone who has a less popular platform is more likely to win, right? Right now, most votes in the states, most voting systems in the states use this first past the post method. Like every state has their own little rules, but it's usually some version of that, right? So about that. Okay, yeah. It also causes this strategic voting, right? Because again, like if there was someone who really wanted to vote for, like, oh man, I really like Barnhill, and maybe some of these other people are they're kind of close, but my heart's really on Barnhill, right? You might not vote your true preference because you have to vote strategically. So, well, how's the entire herd voting? Maybe I have to kind of vote along with them. Otherwise, I really am like throwing away my vote, like throwing away my votes, right? Right. Now, there are like several solutions to problems like that. I'm just going to focus on one, which involves ranking your choices. So when you rank your choices, instead of just checking one box and being done, what you do is you rank your preferences. Say, okay, well, I like this person first, right? But if they don't win, then here's my second choice and my third choice. If you've got like 8 candidates, you can rank as many as you like. So if there's like 3 you really like, you can rank a 1, 2, 3, and then if you don't care about the other ones, whatever, you just stop ranking what you're doing, right? And what that'll do is there'll be some system behind the scenes that it'll knock out the candidates with the fewest number of votes, since I scratch these out, right? And then it'll say, well, who was their second preference? Or, if that goes down, who was their third preference, right? And it'll roll over until someone has like a true majority, right? And sometimes, like this election here, whoever started out with a plurality ends up actually not having the majority in the end, right? So by the first past the post system, Wayne would have won, but by having this runoff system, like this instant runoff, you just want to eliminate the least popular candidates, and you just keep doing iterations of that until someone has a majority. Right? Dravis ended up winning the race that way. Okay. Now for you guys, of course, it was simpler, right? So it made no difference what system. Dravis wins either way. Okay, like I said. All right. Yeah, I've been asking my classes all today if you learn this in any of your like social studies classes at all. I don't know, is this come? No, not at all. Yeah, that's what everyone's been saying all day. Like, right. Well, you guys get to learn that here. All right, so there you go. Science of elections, a little science there. All right. Physics stuff. All right, so you guys know AP Classroom is due on Monday, and have hit, I think most or all the topics that could possibly show up there. Except I need to tell you guys about elevator weight. Right, you guys know if you step in an elevator, here, let me switch my screen over. Got a quick video for you guys. Right, if you step in an elevator, right, you might feel heavy or light depending on which way the elevator is accelerating. This was also one of your mini labs. You guys remember the spring scale lab you guys did? Right. Let's roll this and see how this works. Right. So it looks like the guy weighs like 200, let's call it pounds. It's probably 200 pounds, right? Right. So he's just standing there, right? Elevator doors close. Ooh, and it jumped up to like 220 pounds, right? Now, did the actual gravitational pull on him change? No, right? But it feels really heavy, right? And the scale is shown that, right? That scale is actually reading what force? The normal force. Isn't the floor being pushed into him more than, right? More than his gravitational force pulling him down, right? So there you go. That's the normal force. It's like 220 pounds, right? Now, if you know he actually weighs 200 pounds and the scale's reading 220, you can definitely say that the elevator is accelerating which way? Upward, right? But if that's all you know, there's actually two different ways to accelerate upward. Let's see if you guys remember that. You could be moving up faster, 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 right? Or what's the other way to also accelerate upward? Going down slow into a stop. Yeah, right, right. Now, in this case, since the elevator started at rest, you know it's the first case. You know he's going up faster, 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 right? But if you didn't have that context, then you know it could be either one, right? It'd be ambiguous. Both ways you would feel heavier than usual, right? All right, roll score a little bit. Right. Then the needle jumps down to like 180, which means the elevator is doing what? Yeah, so it's still moving up, but slow into a stop because that's definitely showing accelerating down, right? I bet it feels kind of light. That normal force is less than his weight is pulling down, right? Okay, you guys got it? Right. So let's switch over here and apply some math to that. Actually, I did want to make a connection sort of to your lab yesterday. Right, you guys were out with lab yesterday, right? So you guys were trying out different masses here, saying what's the resulting acceleration, and your challenge was, can you come up with an expression that relates these masses to like these input masses to what's the overall acceleration? Of course, you know gravity though, right? Right, and I showed you two different ways you could approach it. Right? A lot of textbooks, what they'll do is they'll start a system of equations based on these free body diagrams. So say, well, the net force here is causing mass times acceleration for block one. There's Newton's second law of motion. It only is applied to block one. And then you can set up a separate equation for block two. The difference in forces here, the net force causes mass times acceleration for block two. You have two equations, two unknowns. Like if you know what the masses are and you know gravity field, you wouldn't know the acceleration and you wouldn't know the tension force. You could solve for those. The answer, by the way, ends up being this. Right? You guys remember that from yesterday for the classic outwit. Right? Now, how I usually take students through this, though, is start from a systems point of view, right? Like if you got a tug of war between these two, you go net force on total mass, like as a system, right? And from that point of view, tension is just internal to the system. It's just holding everything together. So it doesn't actually show up as an external force, right? It's just internal, right? So the difference in weights is the net force, right? So clockwise versus counterclockwise. Here's the total mass being moved around, right? You could solve it that way. And then if there was a question like what's the tension in the string, then you could take that acceleration and either pop it in here or here. And either way, you'll get the same number for tension, right? Something like that. Right. Now for elevator weight, we can just focus on one or the other. Like this guy right here is like accelerating upward, and this guy here is accelerating downward. So I bet if you were inside either one of these crates, you'd feel really heavy here or really light here. Right, kind of. Right. Now, right before I do that, I should do a numerical example with you guys with this outwit. So let's do a numerical example for outwit, just a little bit of a review from yesterday, and then we'll focus on one or the other elevator and see what's the knock behind that. Okay, so do a little bit of review here. Okay, let's suppose you got let's do how about 3 kilograms here and 1 kilogram here. How about that? Okay, so it's 3 to 1, right? 3 to 1 kilograms. Okay, so let's go with both questions that could be asked. Right? I'm going to say something like, "What's the acceleration?" A key might phrase that, "What's the downward acceleration of the large block?" or "What's the upward acceleration of the small block?" Okay? And the follow-up question could be, "What's the tension in the string holding those together?" Okay? So you guys go ahead and solve that. Okay, somebody tell me, I guess either of those, right? What's the, yeah. What's the downward acceleration of the large block? And then what's the tension in the string, right? If you can figure out either one of those. How about this? Help you guys out a bit. Okay. How many newtons of force is that right there? 30 newtons of force. Okay. How many newtons of force right here? Yeah, 10 newtons of force. Ooh, see how this guy is 3 times the length of that? Right. Okay. Do you guys think the tension is somewhere between those two? Okay. Oh, it's the same tension for both, isn't it? If I do F sub T, like the tension force, F sub T.
Acceleration is exactly 10 meters per second.
It would be 10 meters per second squared if you cut this guy off, right? Then be accelerating down 10 meters per second squared, right? But with this guy, I bet it's going to slow it down.
The A is 20.
Or 20 newtons divided by 4 kilograms.
Actually, what's N?
Right. Right here. Let's do this the way I was showing you guys here. Right. Again, right. Different ways you can do a micro approach with system equations. You can do a macro approach, like systems point of view. I'll start from the systems point of view. Net force on total mass. Right. I'm looking at net external force, clockwise versus counterclockwise. Okay. So acceleration is this is Newton's second law of motion, right? Net force on total mass. So net force, you see 30 versus 10. So it'd be 30 newtons minus 10 newtons, right? Clockwise versus counterclockwise. Okay. And is it 3 plus 1 kilograms? 3 kilograms plus 1 kilogram? Like that, wouldn't it? Right? So I got, what's that? Yeah, 20 newtons on 4 kilograms. What's that going to be? 5 meters per second squared. There you go. It's like half the rate of gravity. Right? Maybe a rule of thumb. You can put that in your back pocket. Right? If these masses are a 3-to-1 ratio, then it will be like it'll accelerate half the rate of gravity. That's an interesting little tidbit, right? Oh, do you guys see this unit right here? Newton per kilogram. Is Newton per kilogram the same thing as meters per second squared? It's the same thing. Same thing. Right? AP likes to do that every once in a while. They'll say, "What's the acceleration?" And they'll have multiple choice answers, and all the multiple choice answers are like Newton per kilogram. Or sometimes they'll tell you so many Newton per kilogram, and you have to recognize, ooh, that's the same thing as meters per second squared. That's an acceleration unit. Okay. Right. So the follow-up question is, what is the tension in the string? Supposedly, either way you do this should get you the tension. Maybe we'll try both. Right? Now, before I start plugging and chugging, how many guys think the tension's probably kind of close to 20 newtons? Maybe about halfway-ish. Maybe not exactly 20 newtons, but 20 newtons would be halfway between these two, right? I bet it's not too far off, right? So maybe I'll pick this guy right here, right? Let's focus on this 1 kilogram. Right? So could I say the net force on block 1 is equal to mass times acceleration of block 1, right? And the net force would be, let's see, the tension up, which we're solving for, minus the 10 newtons down, results in the 1 kilogram block accelerating up how much? 5 meters per second squared, right? Because we already found that, right? So this is 5 newtons here. Add 10 newtons over, and how much is that? 15 newtons. 15 newtons, right? So I made an initial guess of about 20 newtons. Okay, it ends up being a little bit less than that, right? Actually, that's a pretty good rule of thumb too, right? If you like average these two forces, the tension force usually ends up being like less than that. Okay, right? Could I have done that from the point of view of the other block? What if I did the other block? I should also end up with the same tension, right? Let's see if I do. So the net force on the large block could be mass times the acceleration of the large block, right? And that's, see, 30 newtons down minus the tension force up results in 3 kilograms accelerating at also 5 meters per second squared. Now it's down this time, so I switch down to the positive direction. It would work out that way, wouldn't it? Okay. So let's see, 3 times 5 is 15. Subtract that over, add this over. The tension force is, again, 15 newtons. So you could do it either way. Right, guys, see that? Right? You guys can navigate that? Right. Yeah, definitely be comfortable with Atwood's. Atwood's really classic physics question, right? There's no way you can't get an Atwood question somewhere on AP exam. You guys' next quiz coming up. I gave you guys a fancy Atwood. I gave you guys like an incline Atwood. So there's like multiple things going on. Okay, so you guys can fill it out with. Right. Now, if we focus on like one or the other block, it's kind of the equivalent of just an elevator accelerating up or down, isn't it? Okay, so let's do that. Right. Like here, maybe I'll go back to this little guy who's accelerating upward. Can I say okay, let's provide a diagram on that. Right? Maybe there's a guy standing on a scale, for example. Right. Now here I'm showing the tension force, like the tension holding up the elevator cable. Right. You could also say the normal force, like the normal force reading on the scale. Right? However you want to think of it. Right? Tension in the elevator or normal force reading on the scale. What do I do for? I'll call it tension force because that's consistent with my picture so far. Right. Now I'll give this guy a weight down. Maybe that could be the whole elevator weight if we're talking about the tension in the cable holding the elevator. Right. Something like that. So I wonder, like, what's the acceleration? Well, I know that I could say the net force is equal to mass times acceleration, right? In this case, the net force is the tension force up minus the weight down, results in mass times acceleration, right? Now that's kind of what we just did so far, right? I guess there's different things you could solve for depending on what you know so far, right? Like if you knew the acceleration, you could solve for the tension. That's what we just did, right? Yeah, let's go ahead and continue that. Right? Let's get like a general answer because we just did in terms of numbers. In terms of numbers, we got some number answers, numerical answers. Right? But what if we solve in terms of variables? Can I add the mg over and get the tension force is equal to mg plus ma, like that? Right? And then can I factor the mass out and get the tension force is going to be m times g plus a, something like that. Right? Now that expression right there works for upward acceleration. Notice I'm not saying upward velocity, which may or may not be the case. I'm saying upward acceleration, which might be up faster, 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 or might be moving down slow to a stop. Right? Those would be, that could be both of those, right? Is that? Right. So in our example over here, we had 1 kilogram. We had gravity field was 10 meters per second squared. The acceleration was 5 meters per second squared. 10 plus 5 is 15 times 1. Oh, 15 newtons, and we got 15 newtons. Is that, here's the numbers. Here's in terms of variables, right? You guys are getting more comfortable in this class, like solving in terms of variables, right? I mean, it's the same process as it's just, you just leave the variables and just do the algebra that way, just like that. Okay. Hey, do you guys think if you do downward acceleration, it'd be a similar type process, except what do you guys think is the only difference for downward acceleration? Tension force equals mass times what? Instead of g plus a, g minus a, right? That would probably make sense, right? Because look, force has something to do with like some kind of mass times acceleration. Right here, it's like additive. Right here, it's like subtracting. In fact, an extreme example is you just cut that cable. Because if you cut the cable, is that whole elevator accelerating down at the rate of gravity, right? The gravity field. And what is g minus g? 0. So the tension force would be 0 because of course you cut the cable. See how it goes hand in hand? I guess that. Okay, now, what I want to show you guys is that I have a poster version of everything we just did. Right? Well, I don't quite have the proof right now. Maybe we should have made a poster with the proof. Right? So this is like the result. Right? So here's elevator doing one of these 3 things. Maybe I'll start in the middle and branch out. The middle one, the elevator is in equilibrium. Now, equilibrium might mean at rest, or if it's not at rest, it's doing what? Constant velocity. Could that be constant velocity up or constant velocity down? Yeah. In fact, any of those situations, you would feel exactly the same. Suppose you're like standing on the scale right here, right? If it's at rest or moving up at constant velocity or moving down at constant velocity, you would feel the same. The free body diagram is the same, right? And the tension in the elevator cable holding it up is just equal to the weight of the elevator, right? It's the same for all those situations, right? If you're accelerating upward, right now, I just showed you guys the proof for that. I just wrote up, it was just a few steps, right? Oh, look at this. The tension in the elevator cable is m times g plus a, right? Or if you like, maybe the normal force reading on the scale could be m times g plus a for that individual mass right there. And if you're accelerating down, it'd be m times g minus a. Right? Now, if you guys get an FRQ that asks you something like this question, they will expect you to be able to write out this full proof. I mean, it's just a few steps. You guys can start with Newton's second law of motion and just do a few steps. You guys can do that, right? Right. And then there's probably like a point for that, a point for that, a point for that, a point for that, right? You guys have seen enough of these rubrics, right? If there's a multiple choice question, right, and you're under like time pressure, I've only got like 2 minutes per question, right? Could you guys maybe keep these expressions in your back pocket and just whip them out so you can solve it real fast, right? It's probably a good one to know, right? You guys see that? All right. I think that's all I want to say on the elevator. All right, let's do this FRQ. Let's do this FRQ. All right, so there's an FRQ on your desk.